The universe that never stops creating. Every second, somewhere in the vast structure of the universe, something is being born. Not metaphorically, not symbolically, but physically, through the same laws of gravity, pressure, temperature, and nuclear fusion that have governed reality for over 13.8 billion years. Stars ignite, clouds collapse, energy condenses into matter, and matter becomes light. Yet despite centuries of observation, despite orbital telescopes, deep space arrays, gravitational wave detectors, and interplanetary probes, humanity still stands at the edge of one of the simplest but most profound questions. What is the universe actually doing with everything it creates? The universe is not static, it is not a frozen painting of stars scattered across a black canvas. It is a living process, an unfolding sequence of physical events that never stops. In the cold darkness between galaxies, enormous molecular clouds drift silently. These clouds are not empty. They contain hydrogen, helium, dust particles, and trace elements forged in ancient stellar cores. They stretch across dozens or even hundreds of light years. And yet, inside them something is always happening. Gravity never sleeps. Over time, regions within these clouds begin to collapse under their own mass. At first, the change is almost invisible. A slight increase in density, a subtle shift in temperature, a microscopic imbalance in pressure. But given enough time, these small irregularities become dominant. Gravity amplifies them. Matter begins to fall inward. The cloud fragments, and each fragment becomes a potential star. As the core compresses, temperatures rise dramatically. Particles collide more frequently. Energy builds up. Eventually, the pressure becomes so intense that hydrogen nuclei begin to fuse. This is the moment of ignition. A star is born. A thermonuclear engine that will shine for millions, billions, or even tens of billions of years, depending on its mass. From the outside, it looks simple, a bright point of light in the sky, but in reality it is a controlled nuclear reaction on a scale impossible to replicate anywhere in human civilization. Across the universe, this process is repeating endlessly. In some regions, stars are forming rapidly, especially in dense nebulae inside spiral galaxies. In others, star formation has slowed as available gas becomes depleted. But nowhere does the universe truly stop creating, and creation is always balanced by destruction. Every star has a life cycle, a beginning, a middle, and an end. Smaller stars like red dwarfs burn slowly and steadily for trillions of years. Larger stars burn bright and die young. Massive stars live fast and die violently. When they reach the end of their fuel, they collapse, and in many cases they explode. Supernovae scatter heavy elements into space: carbon, oxygen, iron, and everything necessary for planets and eventually life. What remains can become a neutron star. Or if the original star was massive enough, a black hole. A region where gravity becomes so extreme that spacetime itself curves inward beyond a point of return. But black holes are not just endpoints, they are also participants in a larger system of cosmic recycling. This is where the real mystery begins, because scattered across galaxies is not only light and gas and stars, there is something else, something less discussed but equally important: cosmic debris, the remnants of everything that has ever been broken apart. Asteroids, comet fragments, planetary collisions, dust from supernovae, shattered crusts of worlds that never survived their solar system's evolution. Even artificial objects in some regions of space explored by civilizations, though those are insignificant on a cosmic scale. This material does not simply disappear. It drifts, it interacts, it collides, it becomes part of larger structures again, or it is pulled into gravitational wells. And over immense timescales, much of it migrates toward the deepest gravitational centers of galaxies, supermassive black holes. Almost every large galaxy has one, a central object with a mass millions or even billions of times greater than our Sun. And around these objects, something extraordinary happens. They do not simply suck in matter like a vacuum cleaner, as popular visualizations often suggest. Instead, they shape the geometry of space itself. Objects move along curved trajectories determined by spacetime geometry. As matter approaches, it forms an accretion disk, a rotating, heated structure of gas and debris. Friction and compression inside this disk generate enormous energy, so much energy that it can outshine entire galaxies, and yet the center remains dark, a region from which no information escapes. This is the boundary humanity calls the event horizon, not a physical surface, not a wall, but a limit defined by the structure of spacetime and the speed of light. Crossing it means losing the ability to communicate with the outside universe forever. It is not destruction in the traditional sense, it is separation from causal connection. And this is exactly where the mystery of cosmic waste becomes more than just a question of astronomy. It becomes a question about the nature of existence itself. Because if matter falls into a black hole, where does it go? Does it disappear? Does it compress into something infinitely dense? Does it remain forever hidden? Or does it transform into something we do not yet fully understand? To answer that, humanity would need to go closer than ever before, closer than any probe has gone, closer than any signal has survived. And so, a mission was launched, a research vessel known as Horizon. Its purpose was not exploration in the traditional sense, it was investigation, a controlled descent toward one of the most powerful gravitational objects in the known universe. A supermassive black hole at the center of a distant galaxy. The mission parameters were simple: observe, record, survive as long as possible, and try to understand what happens when matter meets the ultimate boundary of spacetime. As Horizon left its home system behind, the familiar light of its star faded slowly into distance. The ship moved into interstellar space, where distances were measured not in kilometers, but in light years. Here, space was not empty, it was structured. Filaments of gas, invisible magnetic fields, scattered dust clouds, and the faint glow of distant galaxies, each one containing billions of stars and countless worlds. The crew observed everything carefully, because every region they passed through told part of the same story. A story of creation and destruction, of matter being constantly reshaped, of energy flowing through systems that never truly rest. And ahead of them, in the direction of a gravitational center that had influenced its entire galaxy for billions of years, waited the most extreme object they would ever encounter. A black hole that had been quietly shaping cosmic evolution since before Earth even existed. And as Horizon continued forward, one truth became increasingly clear. They were not just traveling toward a destination, they were traveling toward the edge of what physics could fully describe: the graveyards of matter. As the Horizon advanced deeper into interstellar space, the character of the universe began to change in subtle but important ways. At first glance, space still appeared empty, an endless black expanse punctuated by distant points of light. But as the ship's sensors became more sensitive and the observation range expanded, the illusion of emptiness dissolved. Space was not empty at all, it was filled with structure. Fields of scattered debris stretched across regions that once belonged to ancient star systems. The remnants of cosmic history drifted quietly through the void, shaped by gravity and time. Asteroids, some no larger than city blocks, moved in slow, stable orbits around invisible gravitational centers. Others had been ejected from their original systems entirely, now wandering interstellar space without a star to call home. Fragments of planetary crusts floated silently, their surfaces scarred by impacts that had occurred millions or even billions of years ago. These were the remains of worlds that had never survived the violent processes of cosmic evolution. And beyond them, finer material, microscopic dust composed of heavy elements, formed faint, diffuse clouds that stretched across enormous distances. This was not chaos, it was accumulation, a record of everything the universe had already done. The Horizon passed through one such region where debris density increased significantly. Instruments detected variations in gravitational influence, suggesting the presence of ancient collision zones, areas where planetary systems had once been destroyed or destabilized. The crew monitored everything closely. This material was not waste in the human sense. It was simply matter without structure, matter waiting to be reorganized. Then, unexpectedly, a new signal appeared on long-range sensors: a dying star. At first, it appeared stable, but spectral analysis revealed its true state. The star had entered the final stage of its life cycle. Its core had exhausted hydrogen fuel long ago. Now helium fusion was slowing. The balance between gravity and radiation pressure was collapsing. The outer layers had expanded dramatically, transforming the star into a red giant. From its surface, vast quantities of gas were being expelled into space. These stellar winds carried newly forged elements outward. Carbon, nitrogen, oxygen, and heavier atoms created in the star's interior over its lifetime. The star was not disappearing, it was recycling itself. Its outer layers would disperse into the interstellar medium, enriching future star-forming regions. Its core, depending on mass, would either become a dense white dwarf or collapse further. But in this case, the gravitational readings suggested something more significant nearby, a region of extreme space-time curvature, a black hole. The crew adjusted course slightly. The dying star was not isolated. Its expelled material was already being influenced by a massive gravitational field in the vicinity. Streams of gas were stretching into long, luminous filaments, pulled slowly in a specific direction. Not violently, not instantly, but inevitably. Gravity does not act like a force that grabs objects abruptly. It shapes motion over time. Everything follows the curvature of space-time, and in this region, that curvature was dominated by something invisible but overwhelmingly massive. As horizon moved closer, the sensors began detecting increasingly complex gravitational interactions. Asteroids that had been stable for millions of years were now slightly shifting their trajectories. Dust clouds were being elongated into thin streams. Even the path of light from distant stars was bending subtly, creating faint distortions in observed positions. The crew realized they were entering the outer influence zone of a supermassive black hole, a region where nothing dramatic happens instantly, but where everything slowly begins to change direction. Then they saw it. Not directly at first, but through its effects. A region of darkness surrounded by a luminous structure, the accretion disk, a vast rotating ring of superheated plasma formed from matter spiraling inward toward the black hole. Temperatures here reached millions of degrees. Particles collided at relativistic speeds, emitting intense radiation across the electromagnetic spectrum. This was one of the brightest phenomena in the galaxy, and yet it surrounded absolute darkness. The paradox was striking. Brightness surrounding absence, energy surrounding a point of no return. The horizon slowed its approach, maintaining a safe observational distance. From this vantage point, the scale of the black hole became clear. It was not a simple object. It was a region of influence extending far beyond what intuition could grasp. The crew observed matter entering the accretion disk. Asteroids disintegrated under tidal forces. Comets vaporized as they approached extreme temperatures. Gas was compressed, heated, and accelerated until it emitted intense radiation. Everything falling in followed a predictable path governed by relativistic physics. Nothing was random. Everything was controlled by geometry. Then, for the first time, the ship's cameras captured a direct visualization of space-time distortion. Stars positioned behind the black hole appeared warped into arcs and rings. Some were duplicated, appearing in multiple positions due to gravitational lensing. Light itself was being redirected, bent around the massive object like water flowing around a rock. The closer the horizon observed, the more extreme the effect became. And at the center of it all was the boundary that defined everything, the event horizon. Not a surface, not a structure, but a mathematical limit, a point beyond which escape velocity exceeds the speed of light. And because nothing in the universe can exceed that speed, anything crossing it becomes permanently disconnected from the external universe. To the outside observer, objects approaching the horizon appear to slow down. Their signals weaken, their light shifts toward lower and lower frequencies, until eventually they fade from detectability. Not because they vanish, but because their information can no longer reach the outside world. This raised the central question that had brought the horizon here in the first place. If matter disappears from observable reality after crossing the event horizon, what actually becomes of it? To answer that, the ship would need to go closer. Closer than any mission had ever attempted. Closer than any human-controlled instrument had survived. The next phase of the mission would involve deploying a probe into the most extreme environment known to physics, a place where time, space, and energy behave in ways that defy everyday intuition. The boundary between known physics and unresolved theory, the edge of the event horizon, the edge of no return. The closer the horizon approached the supermassive black hole, the more the universe itself seemed to change its behavior. What once appeared as distant cosmic scenery now revealed itself as a deeply structured environment shaped by extreme gravity. Space was no longer something passive, it was dynamic, it was curved, and it dictated motion on a scale that overwhelmed intuition. Ahead of the ship, the accretion disk grew brighter and more defined. It was no longer a faint ring of light, but a massive rotating structure of glowing plasma encircling the invisible center. The energy output from this region was staggering. Particles within the disk moved at speeds approaching a significant fraction of the speed of light. Collisions between them released radiation across the full electromagnetic spectrum: radio waves, visible light, X-rays, and even gamma radiation. Despite the fact that the central object emitted no light at all, the surrounding region was among the brightest structures in the entire galaxy. This paradox defined black holes: absolute darkness surrounded by extreme luminosity. The horizon maintained a stable observational orbit far outside the most dangerous region, allowing its instruments to gather continuous data. As they recorded the structure of the accretion disk in detail, something became increasingly clear to the scientific team: nothing in this system was chaotic. Every particle followed a trajectory dictated by gravity and relativistic effects. Even the most violent interactions, collisions, fragmentation, heating, were governed by consistent physical laws. Then came a new phenomenon: gravitational lensing became dramatically visible. Stars positioned behind the black hole were no longer seen in their true locations. Instead, their light was bent around the curved spacetime, producing arcs, rings, and sometimes complete circular images known as Einstein rings. In some cases, the same star appeared multiple times in different parts of the sky, each image representing a different path the light had taken through warped spacetime. The crew observed this silently. They were not witnessing optical illusion, they were witnessing geometry itself. Space was not flat, it was curved so strongly that even light followed complex paths. At the center of this distortion lay the event horizon, a boundary that could not be crossed in reverse, a limit defined not by material structure, but by the structure of spacetime and the universal speed limit. The crew prepared for the most critical experiment of the mission. A small autonomous probe was launched from the horizon. Its purpose was to approach the event horizon as closely as possible and transmit real-time data for as long as physics allowed. The probe was engineered with extreme radiation shielding, high-energy communication systems, and autonomous correction algorithms designed to compensate for gravitational distortion. For the first part of its journey, everything proceeded as expected. The probe descended slowly towards the black hole, guided by pre-calculated trajectories. Its sensors recorded increasing gravitational gradients, showing how space itself was becoming more curved as it approached the center. From the perspective of the horizon, however, something unusual began to occur. The probe's transmission rate appeared to slow down, not due to malfunction, but due to relativistic time dilation. In regions of stronger gravity, time does not flow at the same rate as it does in weaker gravitational fields. Clocks closer to the black hole run slower relative to distant observers. At first, the effect was subtle, then it became pronounced. The probe continued transmitting data. Increasingly redshifted signals delayed communication intervals progressively stretched time sequences. Meanwhile, on board the horizon, the scientific team realized they were observing a fundamental feature of space-time itself. The closer an object gets to the event horizon, the more time appears to slow down from an external viewpoint. Eventually, the probe reached a critical region. Its signals became faint, distorted, fragmented. The accretion disk filled the background of its final transmissions, an immense, violent structure of rotating plasma and electromagnetic radiation. Then the data stream began to degrade rapidly. There was no explosion, no visual rupture, no final burst of energy, just a gradual loss of contact, a fading signal, until nothing remained. The probe had crossed a boundary that cannot be crossed back, the event horizon. From that moment on, no information from the probe could reach the horizon again. Not because the probe stopped existing in a physical sense, but because its causal connection to the outside universe had been severed. The crew remained silent for a long time. What they had just witnessed was not destruction in the conventional sense. It was disappearance from observability, a transformation of accessibility rather than matter. The question that had driven the entire mission now became sharper than ever. If the probe still exists in some form beyond the event horizon, what is happening to it? According to classical general relativity, anything crossing the event horizon continues moving inward toward the central region of the black hole. No known force can reverse that motion. The object is carried deeper into the gravitational well, eventually reaching a region where space-time curvature becomes extreme enough that current physics cannot fully describe it. This theoretical region is often referred to as the singularity. A point, or more accurately, a condition, where density and curvature become infinite in mathematical models. But the crew understood something important. Infinite in equations often means incomplete theory in reality. The singularity is not necessarily a physical object as we understand objects. It is a signpost indicating the limits of current physics. Yet one certainty remained: the mass energy of the probe does not vanish from the universe. It becomes part of the black hole's total mass energy content. The black hole grows, even if that growth is immeasurably small. But just as the mission seemed to reach a purely theoretical conclusion, another discovery emerged. A faint emission pattern was detected near the outer boundary of the black hole system. It was not part of the accretion disk, it was not produced by infalling matter, it was something else, something subtle, something predicted decades earlier in theoretical physics. A process involving quantum effects near the event horizon, a phenomenon known as Hawking radiation. The crew did not yet fully understand what they were seeing, but the data suggested something profound. Black holes might not be completely eternal. They might slowly lose energy over unimaginable timescales. A process so slow that for supermassive black holes it would take far longer than the current age of the universe multiplied many times over. Still, the implication was undeniable. Even the darkest objects in the universe might eventually change. Even they might return something back to the cosmos. And that realization would reshape everything they thought they knew about the final fate of matter. Inside the hidden physics. The detection of a faint emission signature near the black hole changed the atmosphere aboard the horizon. What had begun as a mission of observation was now turning into something far more significant. The data suggested that the black hole was not a completely closed system, not in the absolute sense that classical intuition would imply. Instead, it appeared to interact with the universe in ways that involved not only gravity and classical physics, but also quantum processes occurring at the very edge of spacetime. The crew gathered in the main analysis chamber, where large holographic displays reconstructed the incoming data streams in real time. Faint fluctuations in energy were visible near the event horizon, not originating from the accretion disk, not caused by infalling matter, but emerging from the boundary region itself. This was the key detail. The event horizon, previously understood as a strict point of no return, was now being studied as a dynamic region influenced by quantum effects. According to theoretical physics developed decades earlier, empty space is not truly empty. At microscopic scales, quantum fields fluctuate constantly. Particle-antiparticle pairs can spontaneously appear and annihilate in extremely short timescales. Normally, these effects cancel out and remain unobservable at macroscopic levels. But near the extreme curvature of spacetime around a black hole, something different can occur. One of these particles can fall beyond the event horizon, while the other escapes. To a distant observer, it appears as if the black hole is emitting radiation. This is what theoretical physicists had described as Hawking radiation. And now, for the first time, the horizon was detecting indirect evidence consistent with this phenomenon in a real astrophysical environment. The implications were staggering. If black holes emit radiation, then they are not permanent, they lose energy over time. Very slowly, almost imperceptibly on human timescales, but in principle, inevitably. The crew began running simulations to understand what this meant for the larger structure of the universe. Black holes had long been considered the final stage of stellar evolution, objects so dense and so gravitationally dominant that nothing could escape them. But now it appeared they might also be transitional objects, temporary reservoirs of mass energy. The analysis revealed something even more important. Most of the matter falling into the black hole did not reach the event horizon immediately in a dramatic collapse. Instead, it spent long periods in the accretion disk, being heated, compressed, and accelerated. During this phase, enormous amounts of energy were released. In fact, accretion disks around supermassive black holes are among the most efficient energy-producing systems in the universe. A significant portion of infalling matter is converted into radiation before ever crossing the horizon. This radiation escapes into space. It contributes to galactic luminosity. It influences star formation in surrounding regions. It shapes the evolution of entire galaxies. So, in a very real sense, black holes are not just cosmic endpoints. They are engines of transformation. Not everything that approaches them is consumed. A large fraction is redistributed first. The crew began to reframe the entire concept of cosmic waste. What they had once imagined as discarded material drifting aimlessly through space was in reality part of an ongoing cycle of transformation. Nothing was truly wasted, nothing was truly lost. Matter simply changed form, location, and state. Asteroids became plasma, plasma became radiation, radiation influenced gas clouds collapsed into new stars produced new elements, and those elements would eventually become part of new systems again. The universe was not a linear system, it was a looped process of continuous recycling. At the center of this process, black holes played a crucial role. They were not endpoints, they were regulators of extreme environments. They controlled the flow of matter and energy in regions where gravity reached its most intense expression. And yet even they were not immune to deeper physical laws. The faint Hawking radiation signal suggested that, over extremely long timescales, black holes gradually lose mass. If this is true universally, then the ultimate fate of black holes is not permanence, but evaporation, a slow fading into nothing but radiation. The crew sat quietly as this implication settled in. It meant that even the most extreme objects in the universe were temporary. Even the deepest gravitational wells were not final states. There was always a further transformation, always another step in the cycle. At this point, the horizon received one more set of data from its outer sensors. A nearby region of space showed active star formation inside a molecular cloud. Dense pockets of hydrogen were collapsing under gravity. Protostars were forming. New systems were beginning their long evolution. And within those systems, future planets would eventually form from recycled material. Some of that material may once have passed through accretion disks. Some may have been part of ancient stars. Some may even have been influenced by black hole environments billions of years earlier. The universe was not only recycling matter, it was recycling history itself. Every region contained echoes of everything that came before it. And as the horizon observed this new star-forming region, a final realization began to emerge. The question that started the mission, where does cosmic waste go, was based on a misunderstanding. There is no waste in the universe, only transformation, only redistribution, only change governed by physical law. And black holes, once seen as cosmic endpoints, were revealed to be part of that same continuous structure, a structure without a true end. The universe has no final destination. The final phase of the Horizon mission did not feel like an ending, it felt like a widening of perspective. As the ship slowly adjusted its trajectory away from the black hole's most extreme influence zone, the crew continued to process everything they had learned. What had started as a journey to investigate the fate of cosmic debris had evolved into something much larger, a reconstruction of how the universe actually behaves at its most fundamental level. Behind them, the supermassive black hole still dominated the distant region of space. Its accretion disk continued to glow with immense energy, a rotating structure of matter heated by gravity itself. But it no longer appeared as a mysterious devourer of everything. It was now understood as part of a broader system of cosmic exchange. Matter fell in, energy was released. Some information was lost beyond direct observation, but the universe compensated in other ways, through radiation, through redistribution, through time. The crew reviewed the entire dataset collected during the mission. Every observation pointed to a consistent conclusion. The universe does not store matter in isolated compartments, it continuously processes it. Even the most extreme objects, black holes, are not exceptions to this rule. They are part of it. As the horizon passed through quieter regions of interstellar space, the environment once again changed. The density of matter decreased, starlight became more evenly distributed, the overwhelming gravitational distortions of the black hole faded into the background, but the conceptual impact of what they had witnessed remained. The crew began reconstructing the full life cycle of matter as they now understood it. A star forms from collapsing gas. That star produces heavier elements through nuclear fusion. It eventually dies, scattering those elements into space. Those elements become part of new clouds, new stars, new planets. Some of that material is destroyed in collisions or ejected into interstellar space. Some of it drifts for billions of years, and some of it eventually falls into black holes, where it is either converted into radiation before crossing the event horizon, absorbed into the black hole's mass energy content, or, over extremely long timescales, indirectly returned to space through quantum processes like Hawking radiation. There was no final endpoint in this sequence, only transitions, only changes in state. Only redistribution across cosmic time. The concept of cosmic waste itself became obsolete, because waste implies finality, it implies abandonment. But the universe contains no evidence of permanent abandonment of matter. Everything is reused, everything is integrated into something else. Even black holes, once thought to be eternal things, now appeared as temporary stages in a much longer evolution. The Horizon's mission logs began to reflect this shift in understanding. Scientific language gradually changed from terms like consumption and loss to transformation and redistribution. Even the black hole at the center of the distant galaxy was no longer described as a destructive force. It was described as a regulator of extreme gravitational environments, a structure that organizes matter under conditions where ordinary physics reaches its limits. And as the ship moved farther away, something else became visible in the distance, a faint nebula. At first it appeared unremarkable, just another cloud of gas and dust drifting through interstellar space. But spectral analysis revealed something important. It was enriched with heavy elements, carbon, oxygen, silicon, iron, elements that could only have been formed in previous generations of stars. Inside that nebula, gravitational collapse was already beginning again. New stars were forming, new systems were taking shape, new planets would eventually emerge. And within those systems, the same cycle would continue. The crew realized that they were not witnessing a universe that moves toward an end. They were witnessing a universe that constantly reconfigures itself. No beginning that remains static, no end that remains final, only continuous evolution. Even black holes in the farthest theoretical future would not last forever. Over timescales so vast that they exceed ordinary comprehension, they would slowly evaporate through quantum radiation, leaving behind only faint traces of energy. And even that energy would disperse into the expanding cosmos. Nothing would remain isolated, nothing would remain permanent. The Horizon finally set its course back toward human space, but the mission had already achieved something far greater than its original objective. It had reframed the question entirely, not where does matter go, but how does matter change, because in the universe they had now observed directly, matter does not disappear. It transforms endlessly, from stars to dust, from dust to planets, from planets to destruction, from destruction to black holes, and from black holes back into radiation and space. A cycle without a final stage, a system without a final storage, a universe without a final destination. As the ship's cameras captured one last view of the distant nebula forming new stars, the final conclusion of the mission was recorded into its archives. The universe does not lose anything, it only changes everything, and it does so forever.